Hi all, welcome to the ozone technology course. This will be session 24 and this session will be discussing the following topics. We will be giving you the schematics of the chemical treatment, chemical dosing and consequences chart, the slime and scale buildup, bacteria in the system, biological contamination and control, Legionella growth and effects, scaling and corrosion, problems and solutions, maintenance, and water quality. This diagram in this slide is a typical diagrammatic installation or representation of chemical treatment of cooling towers. We have the water tank, cooling tower, water tank, where the cooling tower is sited, and you have a sump. The water is sucked through the sump and goes to the heat exchanger. This water is cold at a temperature of around 35 to 37 degrees centigrade. Now you're looking at the top view of the system. Now the water that comes back from the heat exchanger, which is hot, will flow into the top of the tower, and its temperature is at about 48 degrees centigrade. Now in order to treat this water, there might be possibly 4 different type of dosing stations or dosing tanks, which each of them will have a dosing pump, and each will dose, one will dose biocide, the other the scaling inhibitors, the third will be corrosion inhibitors, and fourth may be anti-foam. Biocide may be in conjunction with algicide. So they are all dosed through the dosing pump at particular intervals to ensure that each of these components are at the optimum concentration as specified by the manufacturer. If you look at this right side of the diagram, this is a side view where the tank at 37-38 degrees is sited, and this is where you have the fins, etc. The suction fan will suck air from the side to upwards, and this is an air plume which will contain water droplets, which will contain all these chemicals, as well as if there is any bacteria that will be also there. As I did mention, water enters at 45 to 48 degrees, falls down into water spray, the air flows up, cools the spray of water, which has got a very high surface area, and through the air suction, the cold heat is transmitted and transferred into the atmosphere through the hot air plume. From the sump, the cold water goes back to the heat exchanger. There is a blowdown valve. When the water gets to a TDS of 15, 2000, 2200, etc., the blowdown valve opens to allow a drain out of a significant amount of water, and is topped up by raw water. Obviously, when this happens, the TDS will drop, but also will be the chemicals that are wasted through the blowdown. So chemicals has to be added every time there is a blowdown. This raw water will also supplement any moisture or vapor that has evaporated. So evaporation loss is always topped up by raw water. Blowdown loss is also topped up by the raw water. Biocides must be added through the dosing pond continually. Algicides are added to reduce the algae growth. It may be added together. There must be always an optimum concentration of the biocides specified by the manufacturer, so that it will be effective in maintaining the total bacteria count within the council standards, generally below 10 to the power of 4, that is 10,000 CFU colony forming units per 100 ml. There must also be no coliforms or E. coli in the system, and the Legionella must be 10 counts per 100 ml. Additional biocides, which are mainly organic compounds, will increase the organic load. The common biocides that are used are oxidative and chlorine that are preferable, as bacteria cannot be immune to this type of biocide, but they will cause chemical corrosion. Organic or metabolic biocides are generally used. These biocides are manufactured after research as to what type is best suitable for specific bacteria. The biocides enter the bacteria cell and inhibit or impede in bacterial metabolism and stop the bacteria from multiplying. These are generally bacteriostatic biocides, or instantly kill the bacteria through disrupting of the metabolism. Unfortunately, bacteria eventually develops resistance to the biocide, so that it will have to be continually modified. That would increase the cost of biocide. Legionella presence in the cooling tower is a very serious issue, because Legionella spreads and infects the aged and immunocompromised through the plume that can travel for many kilometers down to the surface. The occurrence in Australia is mainly in March to end of April. It appears that biocides at the normal concentrate supplied seem not to be effective controlling the growth, so that Legionella can be present even if bacteria counts are low. Monthly tests are conducted when Legionella are found. The towers are subject to special cleaning and decontamination, requiring a shutdown of the central air conditioning system. The other inhibitors, such as antifoam chemicals added through the dosing pump, maintained to specific concentrations by the manufacturer, scaling inhibitors by dosing pump, corrosion inhibitors also by dosing pumps, and with the corrosion inhibitors, most cooling tower systems will have a sacrificial anodes installed, and these become their anodes in preference to the anodic pipes and other components, and therefore reduce the corrosion rates in the system. A substitute for sacrificial anode is the countercurrent anti-corrosion system. This may be also installed as an alternate to the sacrificial anode, which will produce an opposing currents to the corroding current and therefore reduce corrosion. As you know, when you top up or add chemicals such as biocides, antifoams, corrosion inhibitors, scaling inhibitors, etc., you are going to increase the total organic carbon load, which of course there are different types. You have the total carbon itself, the dissolved carbon, which is generally the colloidal solutions of carbon, or carbon particulates, that means clumps that can form because of the breakdown of some protein matter. And you have the total inorganic carbon, that means carbon associated with inorganic substances. You also have particulates, which can be filtered just as much as can do here, and dissolved organics, it will be the same as this is also dissolved organics with inorganics. This is dissolved organics, total organics. This also can be precipitated or flocculated by chemicals. It must be noted that every addition of any chemical will contribute to increased total dissolved solids or total organic carbon. This in turn will require blowdown and top-up water with more chemicals to be added. This is a chart I have drawn to summarize the problems and the solutions using chemicals as a treating system. You have a problem of bacteria, algae, you add biocide or algicide, you will get a low biocount, but you will increase the TDS, organics and TDS. To resolve the corrosion, you add corrosion inhibitors, you will get reduced corrosion, but increase TDS, etc., and therefore you have to increase blowdown for chemicals evaporation and drift. In order to solve the problem of scaling, you have scaling inhibitors, reduce scaling, and of course increase TDS, and you got increased blowdown and increase top of water and increase chemical costs. Foaming due to chemicals, solution is anti-foaming. You reduce the foaming, but you will increase the TDS in organics, increase blowdown, increase chemical, and increase water top-up, and increase chemical costs. Increased water top-up means it will be the increased dilution of chemicals, which means you have to add more chemicals to top up the chemical loss. If you look into all this, the problems are pretty serious and difficult to resolve just with the chemicals. This is why ozone will become a better solution. There will be always a slime build up on the walls of the tank and the pipes, which we can feel it as a slimy surface. Bacteria will always be attracted to the slime because they are food for the bacteria. They harbor under the scale and protected by the porous scales from biocides. Therefore, no matter how much biocide you add, you cannot totally eliminate the bacteria. It is almost impossible to stop scaling using chemicals. You can reduce it. The purpose of the scaling inhibitor is only to reduce the scales and coagulate the organic matter. It is also impossible to maintain the bacteria lower than 1000 CFU economically without using excessive biocides. Corrosion bacteria residing in and multiplying under the scales may cause corrosion of the pipes, irrespective of addition of your corrosion inhibitors or biocides. The chemicals are normally ordered in bulk and stored in the storage room, so there will be much space and safety concerns. This shows a photograph of the chiller plates, the pipes after removal of the chiller plates. These holes are actually copper tubes through which water passes through, you find that totally blocked by scaling on two sides areas. And here, rust and scaling has taken place in one side of the system. You find that this area is pretty clean. So water can flow through this, but not through these areas. Likewise, this is the dirty area. This has been cleaned up. So you can see how scaling can affect the function of the heat transfer equipment. This is a diagram of the maintaining schedules for chemical treatment. There must be a minimum twice in a year maintenance, cost and shutdown for at least 2 days with no air conditioning systems. You have to scrape scissor tubes or scales using iron pipes or iron brushes. You have the washing tank of slime in deposit. You have to physically rub and remove the slimes and deposits. The color of cooling water will be brown to opaque. The cooling tower, and we have to, during the maintenance, we have to change it to fresh water. So there's a lot of water loss. The cooling tower water is toxic with chemicals and blow down and waste to sewer. Even though the council is not very happy allowing this cooling tower water to go into the sewer or to the drainage system, they have very little choice because the alternate is next to impossible, carrying the water in tankers. The bacteria levels are difficult to maintain and shut down for decontamination if Legionella is present is always an issue. Chemicals added will increase the TDS. You must operate the cooling tower with TDS below 1200, failing which there will be big scale deposits. This is equal to about 4 cycles of concentration, depending on what is the TDS of the raw water, which in here is expected to be about 300 ppm. Addition of water to dilute the chemicals laden water, and more chemicals added to replace spent chemicals. There's a significant water usage and significant chemical usage and costs. This is the end of session 24. Thank you very much for having the patience of listening to my session. The next session, session 25, will be on the principles of application of ozone to cooling towers. If you are new to this session, please refer to sessions 1 and 2 on program details and session 3 to 23, which have already been uploaded. If you like this presentation, please click the like icon and subscribe icon, particularly if you want to be notified of the next session. Thank you and have a very good day.